The form a star takes in the ultimate stage of its life is called a stellar point. Lower mass stars with an inner core less than 1.4 solar masses become white dwarfs, and highest mass stars with an inner core greater than 3 solar masses become black holes. Between these are neutron stars, including spinning pulsars. Massive stars die spectacularly, blasting their outer layers into space in Type 2 supernovae explosions. When a star of more than about 10 solar masses reaches the end of its hydrogen burning stage, it will eventually produce an iron core. Initially, this core is held up by its internal pressure, but when it reaches a mass greater than 1.4 solar masses, the Chandrasekhar limit, it starts to collapse, forming an extremely dense core almost entirely made of neutrons. Supernova detonation occurs when the outer layers of the star, which have continued to implode, impact on the rigid core and rebound back into space at speeds of up to 70 million kilometers per hour. This releases massive amounts of energy, creating a great rise in luminosity that may last for several months before fading. A supernova remnant consisting of the debris will become a nebula. Neutron stars are one of the byproducts of Type 2 supernovae explosions. During an explosion, the outer layers of a star are blown off, leaving an extremely dense compact star consisting predominantly of neutrons with a smaller amount of electrons and protons. Neutron stars have a mass between 0.1 and 3 solar masses. Beyond this limit, a star will collapse further and become a black hole. As the neutron star forms, the magnetic field of the parent star becomes concentrated and grows in strength. Similarly, the original rotation of the star increases in speed as the star collapses. Neutron stars are characterized by their strong magnetic fields and rapid rotation. All neutron stars spin around at a furious rate, some rotating as fast as 700 times a second. Over time, their rotation slows as they lose energy. However, some neutron stars show a temporary rise in rotation rate, possibly due to tremors known as starquakes in their thin crystalline outer crusts. Neutron stars that emit direct pulses of radiation at regular intervals are called pulsars. Most neutron stars emit beams of radiation from their magnetic poles. The radiation may take the form of radio waves, X-rays, gamma rays, or even visible light. Astronomers have discovered around 2,000 pulsars, flashing neutron stars, since the first one was spotted in 1967. These neutron stars have powerful magnetic fields and produce beams of radio waves from their magnetic poles. As the star spins about its axis of rotation, the two radio beams sweep out cone shapes across the sky, causing them to pulse where they sweep across Earth. The slowest pulsars send out about 5 pulses of radio waves a second. The fastest send out 716 pulses a second. There are about 100 million neutron stars in our galaxy. Most stars are made of gas, but a neutron star has a crust of solid iron about 1 kilometer thick. Beneath this is a sea of subatomic particles called neutrons, crammed together by powerful gravity, forming a kind of liquid that doesn't exist on Earth. A neutron star's solid surface is 10 billion times stronger than steel, and its gravity is so powerful that the solid surface is pulled into an almost perfectly smooth sphere with the highest points less than 5 millimeters tall and a surface temperature of about 600,000 degrees Celsius. Its gravity is so great that an object dropped from only 1 meter above its surface would accelerate to 7 million kilometers per hour by the time it landed. And an average man on a neutron star would weigh 7 billion tons. The magnetic field of a neutron star can be a quadrillion times more powerful than Earth's magnetic field. It rotates at the same speed as the star. The field lines curve from the neutron star's magnetic north pole to its south pole. At 15 to 25 kilometers wide, neutron stars are about as big as a city. Compared to other stars, however, they are tiny. Neutron stars are the tiniest, densest objects known and can pack the mass of the whole sun into an area smaller than London. The material that makes up a neutron star is so dense that a single spoonful brought to Earth would weigh more than the entire world population. A football made from neutron star matter would weigh 5 trillion tons, about the same as Mount Everest.